Okay, so good evening, everyone. So let's start with today's lecture. A couple of announcements. First of all, assignment 3 is due on March 12th. No, it's not. So assignment is due 1 week later than what was previous number. Okay. So both the Blackboard and the syllabus page reflect that. And there's actually, it was up last time as well, which I forgot to point out. There's project instructions available at this link. So have a look at the instructions. It's about a page or two. It's just about, it gives you various references where you can look at what types of projects you want to do, just to get an idea of what you want to do. Okay. Okay. So yeah, so it also lists what are the deliverables and how you'll be graded. But it's quite open-ended, so try to make the most out of it in the sense of if you already have some domain knowledge and if you're interested in certain types of data sets, try to double down on that. It's a learning experience, so hopefully you can do something interesting with the tools that you're learning in this course. Okay. So those were the couple of announcements. Was everybody able to submit assignment 2 properly? Okay, so there were 2 questions, right? One was about just fine-tuning and feature extraction. So it was basically similar to the script that's available on the syllabus page, except the number of classes changes from 2 to 10. And you have to take into account that the image size is not 224 cross 224, but there are already, I think, ways to change the image size in the transform functions available. The second thing is you are supposed to also use the ImageNet statistics. Okay, ResNet 18 has been pre-trained on certain types of images. So those images have certain means across each channel, red, RB, and G. So those mean values you are supposed to also use when you use a different data set. Okay. So, but those statistics were given even in that example script on the syllabus page. Okay. So I'm talking about these are the statistics. Actually, if you go to PyTorch's webpage, Torch Vision's webpage on these pre-trained networks, you'll get these numbers. Okay, and also you somehow crop your image to get the sized image. Okay, so I hope you guys did that. If not, go back and just add these additional pre-processing steps and see if the performance is even better. Okay. So before I get into the goals of this lecture and the details, there's a change in the VPN service. So some of you are facing difficulty in logging in to the machines. So who's in Team 7 actually? You're able to log in? No? You are. I see that a user is online from Team 7. Okay, maybe. So try to log in. If request is getting timed out, that means that you're not able to reach that machine. The machines are on. Okay. If you are on UIC Ethernet network, then you don't need VPN. If you are on UIC Wi-Fi or home Wi-Fi, anything else, you need the VPN. So try to see whether you have access. If not, we'll try to fix it. Okay. It's unfortunately I can't do much. It has to be something in between. But we'll see. Okay. Okay, so let's start with today's goals. So whenever you are confused, where are we heading in terms of, are we doing a random walk through all sorts of machine learning models? This is the slide deck that you should go through. Even if you don't know the details, you should go through the slide deck to see what were the goals of each lecture. Okay. So for this lecture, the first goal is kind of primitive. It's basically what is the meaning of generative modeling. Okay. We've already seen an example of a generative model when we're looking at NLP problems, which is latent Dirichlet analysis. Sorry, latent Dirichlet allocation. Okay. We've also seen a simpler model, Ney-based classifier, right? That's also a generative model. So we've already seen generative modeling a little bit, but we'll kind of see other generative modeling motivations today. The second point is we'll try to look at the intuition behind two interesting architectures. Both are for unsupervised learning. The first one is called generative adversarial networks. Okay. And the second one is called variational autoencoders, so the point 2 and point 3. So these are interesting unsupervised learning techniques that you might not have seen before. They are used to generate new samples or new observations from, so given data, do some unsupervised modeling. So hopefully you have some intermediate object, some black box, from which you can generate new samples. Okay. So new samples in this case will be images. That's kind of one of the use cases here. And the last point is just difference between why are there two architectures, prominent architectures. There are many other ways to generate images or generate any new samples, but we'll see the differences between these two. Okay. Any questions about what's happening today? So today we're gonna take a break from supervised learning and think about unsupervised learning. Okay. Actually, we've also seen unsupervised learning before, which is language modeling, and it's a part of assignment 3. Language models are unsupervised in the sense there is literally no labels, but you create labels from the text corpus that you have. So your label, for example, is given the first 2 words. What is the third word? Okay, so you create the label from the original corpus. Okay. Let's see. Fine. So we'll cover this, the goals. We'll try to get to reach the goals in 3 phases. First, we'll try to just get a feel for unsupervised learning landscape very quickly, and then we'll look at first the variational autoencoder. We need to first understand what is autoencoding, what is variational in this, in this idea, and then look at the complete solution, which is VAE, and then get to GANs in the second part of this lecture. Okay. So unsupervised learning. So supervised learning is all about features and labels, right? Unsupervised learning is about you just have features. Just think of you've gotten samples x1 to xn from some distribution over x, right? And the goal is to learn some patterns of the data. The goal is to actually learn the joint, the distribution here, the distribution over features, or the distribution over images. It could be also some other properties of the distribution. You may not know the distribution itself, but maybe you want to know some properties of the distribution. Okay, and I'll motivate this using clustering in the next slide. But the key point from this slide is that there is no objective measure of success. Okay, so whether it's clustering or association rules is fine. So clustering or frequent item sets or spectral clustering or even PCA, dimensionality reduction, there's no objective measure for when you have succeeded and when you have not succeeded. You use your intuition, prior knowledge, domain knowledge to claim that it's something meaningful happening. Okay, same thing with for example, topic modeling. Okay, you don't know when you have succeeded and you have not succeeded. You look at the distribution, topic words. For each topic you have a distribution over words. You look at whether the distributions look similar, different. If they're different, are they concentrated on sports words versus music versus something else? And if so, then maybe you've succeeded. Okay. So what are the tasks that we've already seen? The ones we have already seen are I guess up to this point: clustering, frequent item set mining, dimensionality reduction, and density estimation. Density estimation is just think of it as you've been given a bunch of samples from a normal distribution. You want to figure out its mean and variance, right, from the data. So you've only been given some data. You can assume that maybe it came from a normal distribution by looking at a histogram. Maybe it's one-dimensional data, and then you're estimating its parameters. Okay, that's called that's parametric density estimation. It's a simple, it's one example of density estimation, but there are many other ways to do it, and very complex, interesting area in itself. Okay, density estimation. What we have not seen is or seen very recently is embedding and sampling. Okay, so embedding is this idea of you just have words or corpus, and you're creating vectors for words, and we saw this in the NLP lecture, right? So that's actually an unsupervised learning task. There was no prediction task. We created an auxiliary prediction task, either in word-to-vec, skip-gram model or whatever. But ultimately, the goal was to get these vector representations of words, and then maybe hopefully do dimensionality reduction and look at it in 2D space, whether the words which are similar, maybe words about dogs, words about days of the month, words about other topics, stock market, they're all clustered close to each other in the 2-dimensional space. That's how you would say, okay, word vectors are interesting. Okay. Today we'll look at sampling, by which I just mean that we want to go from data, and again unsupervised data, just features, to some intermediate object from which we can sample new observations. Okay. Let me just spend a minute on on how these, let's say clustering, how is this related to P of X, right? I mean, it's in the previous slide I said, data is generated from some distribution on the features, and all we're trying to get is either the distribution itself, which is what the density estimation is, maybe approximation of that, or we do some other tasks. But these other tasks are essentially some sort of properties of this distribution or the features. Okay. In particular, for example, if you look at this 2D example, right, 2 features, you can think of us looking at it from the top. Okay. And there are 3 clusters here in this example, blue, red, and green, right? So you can think of 3 blobs, 3 sorts of Gaussian distributions, let's say. Okay, just to kind of illustrate, 3 Gaussian distributions sitting with, let's say, mean over here, and maybe mean over here. Okay, so 3 Gaussian distributions, and so clustering is all about, think of P of X as some sort of a mixture of 3 Gaussian distributions, essentially, and you're chopping this, okay, finding a level set. Okay, so think of 3 hills, and you chopped it, you get 3 circles, right? Essentially, or not circles, but 3 ellipsoidal-looking things, and that's what these are. The clusters are essentially, areas of the density, areas of the joint distribution, in this case, areas of the joint distribution between the 2 features, which have high enough probability mass. Okay, that's a view. That's a way of looking at clustering. Okay. Of course, you can only do this in 2 dimensions. If you have high dimensions, hopefully you'll do dimensional reduction and then hope that you got some good clusters. Okay. I think there are a few more examples in the slides, but I will skip it. Market basket analysis is again about frequently co-occurring patterns in the data. So in let's say the data is binary, then you're asking what is the probability mass? When you're looking for high support, high confidence frequent item sets, then you're basically just looking at the joint distribution and just asking, for a particular pattern of binary, items present or not, whether the probability mass is high enough, okay, or the conditional probability mass is high enough, okay. So, and of course, PCA, we have seen this PCA technique before. It's about finding directions, principal component directions in the data by using its data's covariance matrix, centered covariance matrix, taking its SVD or eigen decomposition, and that will give you a bunch of vectors, and those are directions along which kind of the data mostly lies. Okay, the data, for example, could be like for example, in this case, data is mostly in the two dimensions, principal component 1 and 2, and in the 3rd dimension there's nothing. Okay, so this is dimensionality reduction. There's another technique we actually quickly glossed over when we were looking at debugging CNNs, which was this thing called TSNE. Okay, TSNE is another dimensionality reduction technique. Okay, and there are many others. Okay, so it doesn't matter what the name is. If you understand PCA well, then nonlinear dimensional reduction techniques are also easy to grasp. So we use TSNE to when we plotted the images into two-dimensional space. We got the feature vectors, we pushed into two-dimensional space and looked at the 2D collage and saw that similar images are in similar locations. That was this dimensional reduction technique. Okay. And density estimation, as I said, is given a bunch of points, assume a parametric form, and fit a. I mean, it could be parametric, or there's something else called non-parametric density estimation techniques as well, family of techniques as well. So here I'm just fitting a Gaussian, or in this case also fitting a couple of Gaussians, mixtures of Gaussians. And we have seen, or at least people who took 575 with me, we have seen EM, expectation maximization, as a way to fit mixtures of Gaussians. Okay, so it's a problem where you can, it's a problem where you would like to maximize likelihood, but it turns out to be a messy problem if you want to directly maximize likelihood of the data. So you assume something called latent variables, where you assume something called latent variables and then do a different maximization of a different likelihood. Okay, and it still gets you the parameters of the original problem, which is to get the parameters of the Gaussian distributions, right? In this case, 2 Gaussians means 2 means, 2 variances, let's say. So you'll get that. So we'll not talk about EM, but I was just trying to connect it to things you might have seen or might not have seen before. And embedding, actually, I'm going to talk about embedding in the next few slides. So this is an example of an autoencoder, okay? Autoencoder, but we'll go into the details pretty soon. And sampling, we'll also again go into the details. This is a bunch of samples of what do these look like actually? What is it? Pokemon. Yeah. So somebody trained, somebody created this intermediate object. For example, I think it's either VAE or GAN, which we'll see later. Okay, and they sampled, they got images of these Pokemons and sampled new images. Okay, and in fact we'll see some examples with what is called the celebrity faces face data set. Okay, that's something which is available on the syllabus page. So I have given the link to the script. You can run the script on the servers when you get the chance. They don't consume too much of memory, GPU memory, but they do take some time to train. Okay, so we'll train. You can train again to create new celebrity faces, but it's at a smaller scale. You can also do a larger scale sampling of new faces, but the ideas are the same. Okay. So let me directly get to sampling. Okay, that's going to be the context today. So to sample, so what is meant by sampling? We're going to sample from a distribution, right? So there has to be some Bernoulli distribution from which you can sample a heads or a tail, or a Gaussian distribution from which we sample a number, right? So given generally, like given some data, okay, you can, let's say it's drawn from some P subscript D, some distribution, okay. We can, give it, now we only have access to the data. We don't know what P subscript D is. So given the data, we can always potentially try to estimate some model. So that's the subscript M represents model. We can try to estimate a distribution P subscript M such that samples from P subscript M and P subscript D are as similar to each other as possible. So if P subscript D was actually a Gaussian, hopefully from the data you have constructed the mean and the variance of that Gaussian, so that now you know completely the distribution and you get new samples. They are essentially the same. Whether you sample from P subscript D or P subscript M is the same, right? So there are two ways to kind of construct P subscript M, subscript M for model, which is to construct P subscript M explicitly, okay? Or we can construct P subscript M implicitly, and it's just a semantic meaning. What is meant by constructing this model from or distribution from which I can get a sample, either implicitly or explicitly. Okay. think of it as explicitly just means finding, for example, the mean and variance of a Gaussian. So if you're doing parametric distribution estimation, then you can get these parameters and you explicitly figure out what is the mean of my data, what is my variance of my data, and you can sample. Okay. Implicitly means you're creating some intermediate object, okay, where it's not specifically that you're getting a mu and a sigma square, but you can still generate a sample, okay, by starting with some source of randomness. So maybe I flip coins, but ultimately I can generate faces, for example, okay. But there is some object here which, given a source of randomness, can generate a sample for you, okay. Maybe given by a Bernoulli random variable access, it can create a Gaussian sample for you, okay. So just think of it as that as being an implicit object from which you can sample. Okay. So here's a very crude, I guess, a high-level diagram of what's happening. So given data, we of course want to maximize likelihood of the data under some parameter, potentially depends on the which parametric family we're fitting. It need not even be parametric actually. If there are parameters, it's, as I said, it's called explicit density estimation, and there are many names here, but let's not focus on that. What we'll focus today is on doing things implicitly, okay, so getting samples implicitly, and in fact we'll try to do that by using GANs or variational autoencoders, and that's the content of today's talk. Okay, so there are many other names here actually. Sorry, GANs and variational autoencoders. Okay. Yeah, so these two are the blocks that we're going to study today. VAE is listed under explicit branch only because there's going to be some distributional assumptions, and we'll see what assumption we are making pretty soon. Okay. Others don't worry about it. If we understand one or two key techniques, then the others are, we know what the input output is. It's just a question of understanding semantics inside later. Okay. So when should we be okay with having an implicit approach where there is no explicit density function like a mean and a variance, but just some object where you start with some randomness and get some sample? Okay. It's useful if you're doing some sort of a scenario-based decision making where you don't really know. So there, like for example, you are a firm, you want to figure out what are the scenarios of the world tomorrow, of the world as in like your market tomorrow or the next month or the next season. Then maybe you have a huge simulator which can tell you, okay, this is how the state of the world is going to be tomorrow or the next month. For example, maybe there's going to be higher interest rates, there's going to be more volatility in the market, things of that nature. Then based on that, you're going to take some decisions. So in that case, you don't really need an explicit model of the world. So you just need simulations. And given the simulations, you can say, oh, in each situation, what would I do? On average, I can figure out what I would do. Okay. If I know in each situation what is the best thing or what is the average thing I do, then you can somehow coalesce that information into what decision should I take today, for example. Okay. So it's useful in decision making where you can create, simulate, what's going to happen in the future. For example, in self-driving, maybe it can, at every given time step, it can figure out what's going to happen in the future as the car is moving forward. Then, if you have that information, you can probably take good decisions. Okay. You can also do something interesting when you have an implicit object, implicit sample generator. Okay, and one task is what's given here, which is called, I guess, image super resolution. So, how many of you have heard of image super resolution? Okay, image super resolution is a task where it's not exactly a sampling task, but in a sense it is a sampling task in the sense that you've been given a low resolution image. So this is the original, which is not really low resolution, but you've been given a low resolution image, and you want to somehow upsample and make a really high resolution image. Okay, so you've been given some training data from which you created this implicit whatever generator, sample generator. Now, given a low resolution image, that's a conditional on the evidence, the current low resolution image, you get some new sample, which is hopefully a high resolution version of that conditional low resolution image. Okay, so you can So you can see that, so there's things called interpolation, bicubic interpolation in this case, where you can go from the, so I'm not showing the low res image here, but let's say this is the super resolution, increased resolution image. So you can create the, you can increase the resolution by a few other things. In this case, you can also use resonance apparently, but they were showing that, for example, if you use GANs, you get an image which is as pretty perceptually close to the original image. Okay, so the training data did not ever see the this, at least these original images, but it had to be trained on some high resolution images, of course. Okay, and you could do other things, but these depart from the original motivation, which is just sampling from implicit generator, implicit sample generator. But these are applications which require like 1 or 2 steps away from what I just said. So let's understand the core technique, which is how to generate a sample from this implicit generation mechanism first. But if you could do that, then you can also extend it to things like, given this aerial image, you can create actually a map like a tile. Or given hand-drawn images, you can actually get colored images of the same thing. Okay, it's not a database lookup where it's looking up something and generating and showing you a similar bag. In this case, it's actually adding colors and slightly changing it to make it realistic. Okay, so this colors features are all sampled. Okay. So as I said, we'll start with VAEs and then look at GANs. And why did we pick these two? Because of course there's going to be some neural networks involved. So let's get started. So either way, okay, whether it's VAE or GAN, so it's going to build this, when I said an implicit sample generator, it's going to just build this yellow block. Okay, and so the yellow block will have some parameters. Just generally think of it as neural network parameters. What that yellow block will do is it's going to be essentially a neural network. It's going to have access to some source of randomness. Okay, by which I just mean, let's say you can sample from a unit Gaussian. Okay, in 10 dimensions, you get a sample. Okay, take that sample and pass it through this yellow block. Then you'll get a sample. Hopefully, okay, you'll get a sample which reflects your data, which is very similar to your data. So this yellow block is trained on some data, right? So x1 to xn, maybe these are images, or is there something, things like that. Somehow you train the theta, and once you fix the theta, then what you do is start from a source of randomness like Gaussian, get a Gaussian vector z, pass it through this, and then you get a point here, maybe this point or maybe that point, and that point is going to correspond to a new, x new. Okay, so this is the training data. I fix the theta, figure out the theta there, and then I pass a random vector. I get a new random vector. Okay, so the x new is just a deterministic function of z. Okay, but hopefully x new very similar to what the data set I had. Like if the data set was a bunch of images of houses, then hopefully x new is going to be an image of a house. Okay, so that's a very complicated part. I would say non-trivial part. Like how are you going to generate a new image of a house, which is hopefully not from the original data itself. So that's the nice thing about these architectures. Okay, these solutions. And yeah, any questions about the overall landscape? So what is this implicit sample generator? This is what it is, and we'll see how the two techniques will get us this object. Okay, this yellow block. Any questions so far? No questions? Okay.
So the aim is to find a closed generated distribution to true data distribution?
Yeah, so the aim is to find this yellow object which creates p hat of x, which is close to p of x. Yeah. I mean, you can do this. So if you did not think of this generative models, you could have thought about just maximum likelihood estimation. If you know p of x, then you can think of fitting a mixture of Gaussians, things of that nature. That would be parametric. But for images, it turns out that those techniques don't work, and neural network-based approaches work.
So I have a naive question. question.
Yes.
Very nice question. You started with talking about the unsupervised learning.
It is unsupervised. X1 to Xn is some images, bunch of images that was used to find theta. And hopefully that yellow block, once fixing the theta gives me that fixed yellow block, and from there I'm creating X new. That's an implicit way. Okay. So what is that yellow block? It's not just a mean and variance of or bunch of means and variances, right? It's actually a neural network, but it's a deterministic object. So I have to have some source of randomness. So I added some source of randomness to the left. Okay, that's the input to this network essentially. Okay, so let's look at the first set of first way, which is autoencoders and variational autoencoders. So actually, variational autoencoder is the one to generate samples. Autoencoders are not, but we'll just understand what an autoencoder is first. Okay. Okay, so I guess so before getting into autoencoder itself, I just want to kind of flip the idea of a neural network. So far we have seen and going from image to a feature vector, right? So if you just chop off the last layer of ResNet 18, then you got a 512 vector from a 224 cross 224 image or whichever size you picked, right? Now you can also go from a feature vector, or in this case a 512 dimensional vector, to actually an image. Okay, you can do the opposite. So just like you did a forward computation from image to a vector, you can go back as well. Okay, which is to go from a vector to an image. So that's the first, concept that you need to get. And the way it's done is actually involves slightly different operations. Okay, and those operations are called transposed convolutional operations. Slightly different. It's essentially the same as having filters and applying filters on tensors. But you can see that I'm going from potentially a smaller tensor to a bigger tensor, right? So that's the conceptual, leap. But otherwise it's the same type of an idea that you apply. In this case, it's called a decon or deconvolution or transposed convolutional network. And decon is not the right word, only because deconvolution means something else in signal processing and other engineering fields. So all the non-triviality here, the difference from here to the usual CNN that you saw is that instead of max pool, there will be something slightly different, and instead of the usual convolution with strides and paddings, there will be strides and padding here as well, except that you're going from potentially a smaller, like for example, spatial tensor to a bigger spatial tensor. Okay, height and width have maybe potentially doubled. Okay, I don't know if I have an image for that. Yeah. So so how can I go from a smaller dimensional object, let's say in this case a vector, or this is a tensor, but with just two other dimensions being 1 cross 1 basically, right? So how can I go from smaller dimensional object to a bigger dimensional object? Of course, I'm gonna do some it's like projecting, just like projecting bigger vectors into smaller dimensions, you can go from smaller dimensions to bigger dimensions. Okay, and an explicit operation is being shown here, where I'm going from a 4-dimensional vector to a 16-dimensional vector. So all I need is 4 columns and 16 rows, right? I just have to specify what those 4 column, what are those numbers in that matrix. But if I had this matrix, then I can go from 4-dimensional vector to a 16-dimensional vector, right? So it's a linear operation. Yeah, here I've reused some of these numbers and set the numbers in a certain way. But let me actually see if I have that animation. Okay, so let me explain this first. Okay, so let me explain first. Before getting into the details of the deconv operation or transpose conv operation, how am I going to get an image, right? I have a vector. Okay, I have a vector, 100-dimensional or 512-dimensional. I need to get an image, right? So let's say I had only and this was my task. I have to go from vectors to images. Then I can actually find a network to reduce. I can find, let's say, if there was a way to specify this operation going from vector to images, like in the sense the entries of the W matrix that I showed in the previous slide, then all I have to do is to change those weights such that like a vector maybe with arbitrary weights will generate some image type of thing, but hopefully that maybe that image is not similar to the cat's image. Then I have to just minimize the difference between those two, the actual cat image and the generated image, and do backprop basically to update the weights, right? So for example, in this case, I'm just saying that if I have a vector of ones, maybe this is a target image, I can actually find the weight such that the ones map to a target image. Okay. So that was for, let's say, one image. Then I can do the same with multiple input vectors as well. So here I was just saying that, let's say I fix this architecture, so there's some theta that I need to figure out. If I start with a vector of ones, or in fact just maybe a vector which is like 1 zeros, maybe not vector of ones but 1 comma zeros. So given this vector, I want to create a image of a cat. Given some other maybe image of a dog, I can change this vector to something else, maybe 0 1 0 0, and create a vector, create an image of a dog. But they have to share the same thetas, right? So same weights. Okay. So that's the constraint. So you have multiple vectors going to multiple images, except that they're all being transformed by the same thetas, same parameter, same neural network, and these inputs are essentially embeddings, which is what we saw before when we were doing from images to outputs of the ResNet, the last but one layer. And what we're going to do is to stack two things. The first thing is the network that I've just described in the past two slides, which is going from a embedding to a image. Okay, I didn't tell you the details of the decon operation, but modulo that, it's going from a vector to an image. I can also go from an image to a vector, and that is what we already saw. Like if you just use a ResNet pre-trained network, it's going from an image to a vector, right? So that's this part. Okay, and this part is called an encoder, and this part is called a decoder, just in nomenclature. And what we're going to do is to do end-to-end training. We're going to figure out parameter here, maybe theta 1, theta 2, a bunch of sets of parameters on both sides, such that I can pass the original image, get an intermediate vector, and from the intermediate vector get back the original image. Okay, so I'm going to find the theta 1, theta 2 such that these two are the same. Okay. So of course, if I don't do anything, let's say this intermediate vector is actually the size, let's say the image is of size 32 cross 32. And if my intermediate vector is also 32 cross 32, then I can just remember the image and pass it forward, right? So of course, this green box hopefully is a smaller dimensional vector. Okay, like 512 in ResNet 18's case. Okay. So let me get to so let me finish the definition of an autoencoder, and let me see if I can show you the decon animation. So what is autoencoder's perspective? Autoencoder's objective, it's an unsupervised task, just like word2vec. Okay, it's going to find embeddings of images in this example, and we're going to call them, I guess, latent variables. Okay, and the dimension of z is going to be, let's say, something like 512 or 10 or something like that. And we just want to start with, we have a corpus of images, and we start with those corpus of images and pass it through an initial parameters, maybe theta 1, theta 2, get an estimate, get a reconstructed image, compare those two, there will be a loss, let's say mean square error loss, and backprop it to update theta 1 and theta 2. Okay. And what's happening here is that you're going from an image to a embedding. Okay, there is some loss of information. Let's say you picked the cat image, you went to an embedding. there's going to be some loss of information, right? It's not the full image. Maybe it's only 10 numbers, let's say. And from those 10 numbers, you're again trying to generate back the original image of the cat. Okay. Similarly, for the dog, you're compressing it to 10 numbers and getting back the original, trying to get back to the original dog. You may fail, right? If this vector is only, let's say, one dimensional, you're compressing a cat's image to one number, and from one number you're generating a cat. It's probably not feasible. So what autoencoder is essentially doing is picking up some common patterns in your data. Okay, it has to pick up the common patterns in the data, because otherwise it will common as in generalizable patterns in the data, because if it is able to pick that up through this parameter theta1 and theta2, then it can generate images which hopefully look like maybe not exactly dogs, but at least have the same patterns, so that the mean square error is small. Okay, because there's only few parameters, right? So there's parameters theta1 and theta2, and you're going from images to these embedded vectors. Okay, so that's called autoencoding. It's a way to get embeddings of or in this case feature vectors of images in an unsupervised way. If you do this operation, you get these z vectors, and then you can use these z vectors as features in an SVM multi-class classification, for example. So the same thing as feature extraction transfer learning example that you had. Okay. So autoencoding just means that you're trying to encode the input. You're trying to code the input. Code just means converting into an embedding. Autoencode just means you're converting your code and reconverting into the input, and then comparing the input with its own reconstructed version. Okay, that's the auto part. Actually, a few more slides about this, but okay, here's another illustration. Explicitly, I mean, here we just focus the loss function. It could be mean squared error loss. Okay, so going from an input to intermediate vector. So we care about this. Okay, at the end of this whole operation, trained network, we can just use the features. Okay, we can just use the features for some as starting points for some other classification task. Maybe you're also interested in encoding, which is theta1 and theta2, let's say. Maybe images, you want to compress them into smaller sized files, and hopefully you transmit over the network, and maybe on your phone or some on the client side, there's a decoder which can decode that vector and get you an image. Okay, that's also possible. Okay, so what we're trying to do is, as you saw, we are basically reducing the dimension, right? If you choose z to be 2-dimensional or 3-dimensional, you actually get a 2 or 3-dimensional projection of the image, which is 32 cross 32. So it's in that way you can think of it as similar to PCA, but the only difference is that now it's a nonlinear projection. Okay, so it's the first example of something where you're going from an image through a neural network, right? Through a neural, similar to think of a ResNet. So ResNet is essentially a projection of the image to a feature space. If you pick that to be small enough, it's a projection which is nonlinear, right? But that's about encoding features. Okay, so we're getting embeddings of images, but we are not generating new samples yet. Okay, remember, our original motivation is to generate new samples, new images of faces, new images of locations, houses, and so on. So we're not doing that. And let me see if, yeah, so okay. So here I'm just showing you, like, I mean, there are several images like this on the internet. So here we're just trying to show, like, how am I going from a 2x2 matrix to a 4x4 matrix. Okay, so my filter size is 3. The area that you're seeing. Okay, so we're actually not going from the bottom to the blue to the green. We are going from green to the blue, and it's basically the projection operation that I showed you. So we can always go from 14 to 16 dimensional. We can go from 1 to, in this case, we're going to 9 cross 9, 3 cross 3 numbers, and then we're adding them up. So so we can get a higher dimensional vector. Sorry, higher dimensional slice. Yeah.
Yeah. This was in the previous lectures we had done finding the best image for that particular neuron, right?
Yes. Yeah.
Was that using deconvolution?
Yeah, there is a decon operation there. Yes. So I think so let me remember which. So there were several methods that we looked at.
Yeah.
Which one was the one which involved decon? Yeah, I don't recollect.
What
Yeah.
activates the neuron? Like you pass an image and whatever activates the neuron, you keep changing your original pixel using some logic.
Yeah, so that is one. But there was another. So remember, there was this. There was like, what is it called? I was trying to show visualizations of layers, right? So this was the first, I guess, the first version. So that there were like 4 or 5 different variations. The first version involved a decon operation to create those layer, I guess, visualizations. Okay, it's in the. I think the reference is there on the syllabus page. I don't want to go there, but I thought I had a better picture. So there's ways to decon, as in go from smaller dimensional to higher dimensions, and it also involves strides and padding. Okay, so here you are not seeing that, but you can actually add stride appropriate. I mean, here you can see some stride. Right, stride is 1 here, and no padding. But there are ways to add strides and paddings to create a bigger dimensional tensor. Okay, so maybe I will find that image soon, maybe during the break, and explain it better. Okay. And this was, I think, so this was the Pokemon Go creation of images. So we'll get to, I guess, the actual architecture, which is DC GAN, deconvolutional GAN, which as training progresses, it's creating better and better, I guess, looking images. Okay, sampled images. These are hopefully different from the actual training data of original Pokemon Go images. Okay. So anyway, let's get to the variational autoencoder, which is the first our first cut at generating samples. Okay, so variational autoencoder, we need to, I guess, demystify what is meant by variational. It's also a probabilistic extension of autoencoding, which means that there's going to be some sampling, some randomness involved. Okay, the idea is to make Z random. What was a Z? Remember, autoencoder had 2 parts, right? So encoder, so people draw it this way, but the Z over here was fixed. I mean, there was just an embedding of my input images. So if I had 100 images, there will be 100 vectors over there, right? So we're gonna actually try to make a Z random, and in particular, we're gonna try to somehow build a probabilistic model where there's a distribution on Z and it's actually a Gaussian distribution. Okay, that's going to be our restriction. So I haven't told you what the probabilistic model is fully yet, but there will be a probabilistic model where I'll fix this distribution to be to be Gaussian. Okay, so there are a couple of changes. I'll make the architectural changes. I'll make those 2 changes and then tell you what the joint distribution is. Okay. I mean, so what is the joint distribution now? The joint distribution is going to be something to do with x's. Remember, x's, whenever I have unsupervised data, there's always going to be an implicit assumption that they came from p of x, right? Some distribution p of x. Now I introduce another distribution, which is the distribution of the embeddings, or the distribution of these latent variables. Okay, so the joint when I say joint distribution, it's a distribution between these 2. So actually, we'll start with the loss function. So previously there was a reconstruction loss, right? It's just a sum of the squares of the 2 images. Okay, just a pixel-wise difference between how the first image looked like and the reconstructed image looked like, a square of that. Okay, there's going to be second loss function, in the sense that just think of, you had the loss function and you had regularizer before in a supervised learning task. Here there's going to be a loss function, the usual reconstruction loss function, but there's also going to be something called a latent loss. Okay, just a name for that, second term. So there are 2 terms in the loss, and this function is gonna this scoring function is gonna capture how far from the Gaussian distribution the distribution of Z is. Okay, so we want the distribution of Z, which is the output of the encoder, to be Gaussian distributed, but in general it may not be. So think of it this way, right? So let's say there are arbitrary parameters on the encoder side, right? So there's p of x here, some parameter theta, I guess I'm using theta 1, some parameters, fixed parameters. Then there's going to be an induced distribution over here, right? There's going to be an induced distribution over here, p of z. Why is that? Because input is a random variable, some linear not linear, but non-linear transformation of it. There's going to be some output random variable. So given the input random variable, the some distribution, there's going to be output distribution. It's just a function of a random variable is a random variable, right? So, but this is fixed. We can't really change it. P of x is some input distribution that we don't know, but fixed unknown. So P of z for as we pick thetas may not correspond to a Gaussian distribution. So you want to pick those thetas such that the output, the z P of z corresponds to a Gaussian distribution. Okay, that's what I mean by, and we're going to measure that by using some sort of this thing called second loss term, which is called latent loss. Okay, and the loss function is going to be measured in terms of what is called KL divergence. I'm going to tell you what KL divergence is in a couple of slides. And in particular, what we'll try to generate is actually for a given sample, we are not going to generate so we are not. So remember this block, the yellow block from few slides ago, is not really random, right? It's given theta, fix the parameter theta is just some deterministic transformation going from some image to some vector, right? So, but we want some randomness. So what we're going to actually generate on the right hand side of this yellow block is the mean and variance of z. Okay, if I can generate the mean and variance of z, then it's a Gaussian distribution. I know the mean, I know the variance. I can get a sample. Okay, and then pass the sample to the decoder. So there is some randomness that I'm introducing. This is how I'm introducing the randomness. Okay, so from a given x, I can get to the mean and variance of z. Okay, for different x's, maybe there are different means and variances. But given the mean and variance, I can sample, and then I can create I can decode it. Okay, so there's randomness here in the output of the encoder.
But if I'm imposing a Gaussian distribution on the vector, am I not including a bias?
Yeah, I mean bias is basically my restriction on models, right? So everything is like when I think of linear models, it's a restriction, it's a bias. Yeah, it's a.
Like we are assuming the embedding to be a Gaussian distribution.
Yeah, we want the z's. So we want this to be Gaussian. So you can pick other distributions as well. So if you're asking whether making this Gaussian is restricting the expressiveness or the complexity of this model, it's not an assumption. It's actually extremely critical to have this work. Okay, you can have other distributions here, but you have to assume some parametric distribution there. Yeah, because you need to sample. So in this case, I'm gonna generate mean and variance from which I can sample. You can have other real value distributions or even discrete distributions there. Discrete may not make sense, but other distributions there and a sample from that. Yeah. You can have mixtures of Gaussians there. Yeah.
In the Pokemon example, like if we have that input side, if we learn that distribution and take some sample and give it to the decoder.
Yeah.
Create some new Pokemon.
That's what we saw. Right? I mean, did not create new Pokemons, but that illustration that we saw was not for VAE. It was for GAN. We'll see that after the break, after some time. But the point is, you had a bunch of Pokemon images. You trained this network, maybe theta 1, as well as the decoder network theta 2, such that and these theta 1 and theta 2 are such that in the intermediate part I could create the mean and variance of a random variable. Then I'm getting a sample from that, and if I pass that sample through the decoder, I'm getting an image which was not there before. Okay, if the image was already there before, there's a particular there's a particular mean and variance I'm getting, and so therefore the mean is roughly representing that particular sample. But if I generate a different so if I pick a different z, I mean, forget about the encoding. If I pick a different z, I can get a different image which will look like a Pokemon. It may not be exactly like a new Pokemon, but yeah. So what's happening? We're going from, so this is the usual, think of it as like ResNet. You can just interpret the first 100 dimensions as the mean, and the next of course it has to be like n times n squared by 2, some sort of a covariance matrix, right? So all I'm saying is this part you can think of it as ResNet, as just an illustration, okay, as an encoder, just for an example. Then if it was ResNet 18, 512 numbers, then you can pick some numbers as the mean and the remaining numbers as capturing your covariance. I mean, of course, covariance has to have if it's 10 dimensions, then there is order 100 numbers, but there is repetition, right? The covariance matrix is symmetric, so you just account for that. So whatever numbers you have, you want to pick certain mean and certain covariance. Okay, that will determine the output size. Okay, so those are those two vectors, and from which you will sample a vector from this Gaussian, right, and then pass it forward, and then you're going to evaluate. You will get some image, and then use usual reconstruction error. Okay, so you will compare this with this, and you'll also compare whether this looks like a Gaussian, right? So what is this? Latent loss. There are two losses. One is the reconstruction error, and one is the latent loss. So,
but you're assuming that there exists a mean of vector and a standard deviation.
I'm outputting a mean and a standard deviation, but it has to represent. So this is actually the conditional probability, right? This is the probability of z given x. Okay, at a given theta, which is I guess just let's say this is called theta1. So I'm saying this has to be close to a Gaussian, which is with some mean mu and I guess sigma square. I mean whatever sigma.
So and this mean and this mu and sigma should follow the mean vector and the standard deviation.
Yeah. So this, if you change thetas, this conditional probability will be different, right? So now all I'm saying is, yeah, I mean I'm producing two things, but I want a. So this is the assumption I'm making. So I pick theta such that I don't have flexibility in x's. So given thetas, this will correspond to some distribution. This part, I'm just saying that should be a Gaussian.
That's what I understand. So
yeah.
I was wondering whether this probability of z given x comes before mean vector or where exactly. So it's basically some numbers. If we think of a discrete base, some numbers corresponding to each point. If probability of z given x is going to be some numbers. If we think of a discrete case, two cases, it's going to be 0.5, 0.5.
Yeah, yeah.
So this 0.5 coming after encoder network, or it's coming?
No. Probability of z given x. This part is. This is nothing to do with the encoder. So encoder is a transformation, which is this theta1 is this theta1. Okay. So given x, this whole random. So what is random here? So here till here there is sampling, right? So till here is the p of z given x. Okay, let's see. Actually, in the next few slides, I have the expression. So I hope I did not use a different symbol there. So okay, what was it? So I guess in the previous few slides, I just described what the loss function is. Loss function is now two parts: a latent, something to do with Gaussian assumption, and something to do with reconstruction. And the second thing was how the architecture looks like, where I'm saying that if you've trained these things, these two parts, theta1 and theta2, let's say, encoder and decoder, then this is how you would create a. I mean, not this is how, but like if you had training data, then you would pass an image, get some mean values, get a sample, and then pass that sample forward and get a reconstruction. Okay, that's the operation in training. And in I guess if you want to generate new samples, you drop the encoder. Okay, and you just create a z, arbitrary z, and then maybe you'll get an image. Okay, those are the two things. And we'll not go into the details probably about backprop, but you can actually backprop. So there were two losses, right? Loss 1 plus loss 2. You can actually backprop to find the gradients of these guys with respect to both the parameters theta1 and theta2. Okay. There's really not much of a detail. Maybe I can see if I have time, I'll describe. Okay, it's just a two-step thing. Okay, it's called, if people are interested, it's called the reparameterization trick. Okay, it's called reparameterization trick, but it's just a two-line tangential thing. Okay, so because we are sampling, so in training, when we pass that image, we created a mean and a variance from which we are sampling a z and then only passing that sampled z to the through the decoder to get a reconstruction. So this sampling is essentially Gaussian noise, right? Given a mean and a variance, you are adding Gaussian noise essentially, right? And so it's ensuring some sort of a generalization. It's basically saying I don't want to just remember my training data, or just not just the embeddings of the training data, but I want to create some general embeddings, okay, some noisy embeddings. And this is something what I just said. Okay, so this is I don't think I shared an example of a VAE based code in the syllabus page, but there is actually a PyTorch VAE example on MNIST itself. I didn't run it beforehand, but this is an example of samples generated during training, left and center, and this is the original data. So you here it's not clear, these are samples generated, but you can say, oh, maybe it's just doing dictionary lookup or just retrieving an image and showing it. But you will see that for faces and so on, you can actually still do this. So for example, these circles here don't actually correspond to any circle in the training data. Maybe we'll have to check, but so what is the model? So now let's get into the model part, because there is some joint distribution between x and z that I'm assuming, right? So x represents image, z represents this latent variable. Okay, both are going to be random variables. We want to estimate theta star. And what is theta star? It's the conditional probability of x given z. Okay, and there is actually a true distribution on z. So so ignore the Gaussian assumption. Okay, I have some distribution on x's, right? P of x. Let's say I also have a distribution on z's, which I ignore the Gaussian, is some distribution. Okay, then I can get the sample x, or basically, yeah. So this is just a degenerative view where I sample z from some marginal probability, in this case, is distribution over z. And then given that z value, I can sample x. Okay, it's just saying what are the ways of generating x's and z's together. Okay, you can first sample from z, and given z, I can sample from x. That's kind of obvious because the joint distribution is just a product of the marginal times the conditional, right? Basically, p of xz is nothing but p of x given z times p of z, right? So I'm just saying, get a sample here, get a sample here. That would be a sample pair for the joint distribution. But ideally, we want to estimate theta star, whatever is the parametric parameters for this joint distribution, theta star, right? And that's why I just wrote theta star here, theta star here. But now we're going to make an assumption that, okay, I don't know what theta star is, but I'm going to make an assumption, which is essentially called the variational assumption, that P of z is Gaussian. Okay, and I'm also going to assume that P of x given z is a neural network. Okay, so in the previous slide, I'm just saying that this part is going to be a neural network. Okay, and P of z is Gaussian. Okay, those are the assumptions, and given that, I can just think of, so z's are not observed. So I said there is a joint distribution between x and z with some unknown parameter theta, but I never observed theta. In my data, there's some just x's, right? Just some images. So what do? Even if I assume, given the joint distribution, I can always compute the marginal, which is p of x, right? Which is just sum over all these z values. Ideally, I want to maximize this likelihood. P of theta, so P of x is what I want to. That's the likelihood of the data, right? Data is only x's. I have, if I assume some joint distribution, I can marginalize out z, and that's this integration operation. Okay, this is just a joint distribution, by the way. This is nothing but saying integration over p of x and z over z will give me p of x, and that's the likelihood of my data, and that's what I want to maximize. Okay, and okay, and encoder being probabilistic is important. Okay. Wow. Okay, so another thing. So I said p of x z be a neural network, right? So it's a decoder we saw in the in this slide itself. So going from x to z, I said it's a neural network. But then x is not random, right? So given z, x is just a determinacy function. If I say it's a neural network, there's nothing going on. I mean, if once I sample z, if I pass it through a neural network, I'll get something deterministic. So actually, let's make probability of x given z also Gaussian with some mean and variance. Okay, so that now I have something z which is random and x also which is random. Okay, so it's just so that this is also a distribution. Otherwise, it's just a transformation of a random variable. If I just use a neural network as a decoder, right? So I want this is a random variable, this is a random variable. So that's what I'm saying, that let's assume that p of z is Gaussian and p of x given z is also Gaussian, and that's represented here. Okay, just focus on this part. Sorry, that's not that part. Actually, focus on this part. Scratch this. Where I have z. Okay, I'm saying that p of x given z is going to be some normally distributed random variable, where I'm going from z to means and variances. I'll get using the neural network, and then given the means and variances, I can get a x. Okay, that's what, you know, this part is making x random variable. Okay, and similarly, on the encoder side, I'm going to start from x, and I'm going to pass it through a neural network. You remember we just discussed this. That will give me a mean and variance, and from there I can sample a z. Okay, right? Given the mean and the variance, it's a Gaussian, so I can sample from the Gaussian. Similarly, given a z, I can pass it through the decoder network, get some means and variances, I can sample, and I'll get an x. Okay, so those are the two parts. Okay. So what do we need to do is, because we made normality assumption, and mu's and sigmas on both sides are just functions of, you know, what would be a mu and sigma is just depends on the neural network, right? For a given z, let's focus on the left side, so right hand side. Given a z, all I want to compute is a mu and a sigma. Okay, that's like a transformation. Given a z, tell me what a mu and sigma is. That's completely determined by the neural network, right? Yeah.
So this randomness in x given z is coming from the neural network.
Yeah.
So it's following a normal distribution.
No. So neural network is just a transformation. So it's going from z to these means and variances. And if you draw a sample from this mean and variance, which is a Gaussian distribution, you get a random x. So the randomness is not in the neural network. Neural network is a fixed thing, right?
Yeah, sure. So
yeah.
That's why I'm a little bit confused, because given z, x is still a normal distribution.
X is random, yeah. So I want to make both x's and z's random. So in this model, I have to think of some sort of a joint distribution. So I only had x's, my data. I want to think of a distribution on this x only. But in this modeling framework, I'm going to think of a latent variable z. I'm going to think of a joint distribution between them. Okay, it's such that the probability of the latent variable given x is normal. Okay, and the probability of the x given the latent variable is also normal.
So this one I understand, but this one is not.
Which one do you understand? This from a latent variable?
I do not understand, because so it's saying that this is distribution of x given z should come from some randomness in the model. For a fixed z,
yeah.
Given that the neural network is passing just a deterministic
some theta
function,
2. Yeah.
So I do not understand where this randomness is coming from.
No, I'm predicting the mean and the variance, and given the means and the variance, I'm sampling from a Gaussian distribution. So there's random. It's random, right? So do you think x is going to be deterministic if I give you a z? It's not, right? So I'm first predicting. So think of it this way: from z, I'm getting only the means and variances of a distribution, and from which I'm sampling x. So x is random, right?
I see. Okay.
Yeah.
Z is a distribution.
No, z is a random variable, x is a random variable. Okay. Z and x's are random variables. So where did z come from, right? So I'm just saying that we had data. Ideally, we just think of some distribution over x. Okay, x is all the data is just realization of the x. Now we have tacked on another thing, which is this latent random variable z. Okay, and we are going to interpret. So we saw the architecture where there was some encoding and decoding going on. So the z is some object in between, right? So now we're going to say, okay, this z is the random thing that we're tacking on, and we'll try to ensure that the distribution of z given x is distribution of z given x is random. Random as in Gaussian, like this, and distribution of x given z is the Gaussian like this. Okay. I mean this Gaussian. So these are conditional distributions. Remember, the original data may have whatever distribution it has. P of x is not known. Okay. So we don't know p of x. We said let's pick p of x z such that p of x given z is something like this, and p of z given x is something like this. Okay, that's yeah.
How is neural network treating that?
Neural network is a fixed transformation going from x to the mean and variance of the conditional probability. Just these two, and here also given a z, it's only giving me the mean and variance. From there, I am saying if it's a mean and variance of a Gaussian, I can sample from the Gaussian. Some fixed vector. No. So input. So it depends on which. There are two neural networks here. So think of the decoder. Okay, decoder is on the right side. This is the decoder. Okay, the input is some vector z. Okay, 100-dimensional vector, some fixed numbers, bunch of numbers. Okay, so given those 100 numbers, I'm going to create let's say a mean which is of 10 dimensions and variance which is 10 cross 10, 100 numbers. Okay, so total 110 numbers. Let's say modulo some redundancy. And once I get these numbers, I can draw a sample x. Why is that difficult? Because given mean and variance, I can draw a number, right? Given this part. From z, I'm deterministically transforming to a mean and a variance. That's the deterministic neural network part. Getting the mean and the variance, I'm getting a sample from that. Sample from given the mean and forget about the network now. You have a mean and you have a variance. You can draw a sample, right? Yeah. Neural network is just going from z to the means and the variances. That's it. It's a deterministic, I guess, transformation, right? So there's no randomness in the neural network parts, the yellow blocks itself. Remember, if you get confused, just go over to the first slide. The yellow block is just going, transforming some randomness, input randomness to the output randomness. Okay, so it's just a deterministic transformation. Okay. So, okay, what are the next few slides trying to say is mostly like we're getting into the details of what exactly the loss function looks like. I said there is some reconstruction error and some latent loss, right? So I'm gonna motivate like why is this loss? Because what we care about is, so at this point we just said, okay, I'm gonna think of some fake or basically hallucinated variables z, and think of my data is coming from x's and z's, this joint distribution of x's and z's where these assumptions are made. Okay, under this assumption, I only have data. I want to maximize the likelihood of the data. Okay, if you have a idea about the joint distribution of the data or distribution of the data, you maximize the likelihood of the data. Okay, and what are the parameters to tweak? These are the parameters, theta 1 and theta 2, the parameters of the neural network. Okay, that's the only things that are things you can change. Everything else is like predetermined, right? So you want to maximize the likelihood of the data by changing the parameters of the neural network, two neural networks in this case. Okay, and to do so, before I tell you what the likelihood objective is, I want to tell you very quickly a couple of definitions, which is just things for us. We just need to know what these names mean. Okay, okay. Let's not worry about information, but entropy is given a distribution is just the sum of the probability sum over all the values that little x takes probability of that little x times the log of the probability of that little x. Okay, you must have seen this in I'm not sure if you saw this in decision trees, where there was a Gini index, and maybe you also used entropy measure as a measure to figure out which variable to split on, right? So that's just an entropy. So if you're discrete random variable, just compute this number. It's a single number. Okay, and very related things, just very similar. If you see, there's no minus sign here, except there's a denominator which is a q of x. Okay, so this is called KL divergence. KL divergence. Okay, it's written as in this way, and there are many other ways to write the same notation, but it's basically a function of two distributions through two probability mass functions. Okay, it's basically the same as entropy sum over little x. Both probability mass functions hopefully have the same support, as in probability of 1 is equal to something in for p, then probability of 1 is equal to something for q as well. So the both are, so think of it as like this, right? So this is p of x for x is equal to 1, 2 and 3. Let's say this is p of x. Similarly, q of x would be something else, maybe, okay, for 1, 2 and 3. That's it. So given these two p density functions or probability mass functions, you can compute this number. Okay, this number is going to be 0 if p is equal to q. Okay, because if p is equal to q, then log of 1 is 0. Every other time, it turns out that this function is going to be this scoring function, this some sort of a measure between two distributions. It's always going to be positive. Okay, so it's some sort of a dissimilarity between two distributions. Okay, and we need this because, as I said, there's something called latent loss. I said we have reconstruction error and we have second loss. This is just to motivate what that latent loss looks like. Okay, the second loss function looks like. So any questions about KL divergence definition? I mean, we're not going into the details of it, but this is the definition. Okay. In the next few minutes, we're going to go through some notation, but we'll see. I mean, each line is explainable. So what do we care about? We assume some joint distribution over the data, but we care about maximizing likelihood of the data. Likelihood of the data for, let's say, the ith observation is log likelihood is just a log of p of xi. So I got some xi in the sense that I have the ith observation. Okay, x superscript bracket I is the ith observation. I want to maximize its likelihood. Okay, maximize its likelihood. Likelihood is just the probability of that data point given the current parameters theta. Okay, given, let's say, the networks are fixed to theta 1, theta 2, collect them together, call it theta. Okay, so given the current theta, there is some probability of that x that I observe, right? Log of that. Okay, what I'm going to do is just retain the same term, but take an expectation with respect to some other random variable z. Okay, why is this a valid operation? Is because the thing inside the bracket has nothing to do with z, so I can always put an expectation over z. It's like saying expectation over some random variable z of a constant, let's say 10, is 10, right? So I'm just saying that, let's say 10. Let's say left hand side is the number 10. I'm just saying that number 10 is the expectation of a random variable z with that argument being 10. This is obvious. This is just a simple thing, right? There's no computation needed. Then what we do is, so what we are trying to do in the next few steps is to define what that, the latent loss and the reconstruction loss. Okay, so the way we're going to do it is start with the likelihood. This is what we want to maximize over the parameters, and we'll show that maximizing the likelihood over the parameters is the same as these two losses, minimizing the two losses. Okay, so next what we're going to do is add this conditional probability of, we'll add, p of x, we'll just use base rule. So p of x is p of x given z times p of z. This is just a p of x comma z, right? Divided by p of z given x. Okay, this is just base rule. You can take the denominator to the left hand side and bring the left hand side to the denominator. It's just a base rule. Z given x is probability, joint probability between them divided by p of x, right? So that's what we did here. Okay, we just changed these things, but now see what we did is actually previously this was just p of x. Now we introduce z. Okay, so now z and z, there is something interesting going on. Okay. Next, what we do is again, so base rules is fine. Then we add q, okay, which is q of z given x. It's just multiply and divide by something. Okay, multiply and divide by the same number, it doesn't matter, it's 1, right? So we added that. Okay, then we, it's a log of some lot of terms, right? Log of there are three terms in the numerator, this one, and 2 terms in the denominator, right? It's a log of a times b times c divided by ef, right? Log of a b c divided by ef. We're going to split it, okay? And we're going to use, we know that log of a times b is log of a plus log of b. We know that log of a divided by b, also we know a log of a minus log of b, right? So we're going to retain the first term, which is the conditional probability of x given z, okay? We're going to pick this guy, oh sorry, not that guy. Okay, we're going to pick this guy and this guy, okay, where I put 2 pluses here. Okay, we're going to pick those 2 guys, okay, and we can see that the outer expectation is just expectation. It's just a log of the denominator divided by the numerator with a minus sign in the front. Remember, log of a divided by b is minus of log of b divided by a, right? So we have this term here, and then what remained is the one with the minus here, and the one minus as in like those 2 things which I pointed out. Those 2 you just retain as it is. That's this term, okay? So why did I do this? This is just a manipulation with logarithms and bringing 3 different terms. And from these 3 terms, I'm going to drop some term, one of these terms, and then call one term the reconstruction loss, the other term the latent loss. Okay, that's the goal. And the reason why I introduced KL divergence in the previous slide is so that to make notation simpler. Maybe it did not make it too simpler, but this term, last term, is a KL divergence between Q phi and P theta. Okay, so KL divergence between these 2, and the second term is the KL divergence between Q phi and P theta, whereas P theta is just the marginal distribution of z. Okay. Is this part clear? This is definition of KL divergence. This is the definition of KL divergence, which was in the previous slide. Okay. So if you're not sure, how we went from here to here, don't worry about it. It's just a substitution of definitions. What we care about is now understand this part, which is that. Okay. So I copied the same 3 terms into the next slide. The first 2 terms are a lower bound to the data likelihood. Remember, the left hand side was data likelihood for a given observation, ith observation. This is likelihood. The first 2 terms are lower bound because the third term I can drop it. The third time I can drop it because it is a KL divergence between 2 distributions. It's always going to be positive unless the 2 distributions are the same. Then it's 0. Okay, that's a property. We did not prove it here or anything, but that's basically the intuition. So we can drop it. Okay. So maximizing the log likelihood of the data is the same as maximizing these 2 terms. Okay, maximizing the first term minus the second term. Okay. Now remember I said P of x given z. I'm going to make it normal distribution. I'm going to make the normal distribution assumption, right? Remember I said P of x given z is normal, P of z given x is normal, right? So because I make this normal assumption, log of something which is normal is going to just involve the exponent, which is something like a squared loss. Remember there was a log of e to the power minus y minus mu the whole square divided by sigma square, let's say. If you take the log and exponent cancels, and there is a negative of y minus mean the whole square, right? So all I'm saying is this term here boils down to something which is a squared, so first of all, we want to maximize the likelihood. Okay, likelihood. Maximizing likelihood is the same as maximizing these 2 terms on the right hand side, right? This term and this term. Now I'm just saying that maximizing the first term is the same as maximizing minus of y minus mu the whole square. It's the same as minimizing y minus mu the whole square roughly, which is the reconstruction error. Okay, so the first term is essentially the reconstruction error because the Gaussian distribution's exponent and the log somehow cancel, and maximizing the negative of the Gaussian distribution's exponent is the same as minimizing the reconstruction error, which is some sort of a squared loss. Okay, that's what I'm saying. So first term somehow gives us the squared loss, and the second term is the KL divergence between the conditional probability of KL divergence between Q of z given x and the marginal distribution of z. Okay, so that is called the latent loss. Okay, so that latent loss is being measured in terms of KL divergence. So that's why I introduced KL divergence before. So first term is some sort of a mean squared error. That's all I'm trying to say. And the second term is essentially KL divergence between two distributions, where the first distribution is the encoder distribution. Okay, and the second term is the marginal distribution of z. Okay, and we want to maximize the likelihood is the same as maximizing these two terms or minimizing these two negative of these two terms. Okay, so just to summarize before we take a break is that we have some input data. We're going to pass it through a network, our encoder network. It's going to give us two vectors. I mean, let's say we got a huge vector. We can always reshape it and make one part a variance matrix and the first part as like mean. From there, I'm going to get a sample. Okay, from this Gaussian distribution, pass that sample through again a network, my decoder network, get another mean and variance, and then draw a sample from that. That's my x hat. I'm going to compare x hat with x. That's during training. The first term is going to compare x hat minus x the whole square. Essentially, that's my reconstruction error. The second term is going to compare whether the distribution of the distribution induced by my data is close to Gaussian or not. The second term is the KL divergence between the Q of what is this Q of phi of z given x compared to p of z, right? So p of z, I'm saying I wanna say that p of z is Gaussian. Okay, so that's how you get the two terms. And if you really want to visualize, this is the encoder, the usual ResNet type of usual convolutional neural network. This part involves decon. As I said, you can always go from lower dimensional things to higher dimensional things, except visually they look like convolution operations. That's why they're called transpose convolution operations. And they also involve some stride and padding. Okay, the details are not really critical. I mean, as long as you understand that you can go from a low dimensional vector to a high dimensional vector, which we saw, right? Any vector we can go to a higher dimensional vector. That's linear transformation, right? So if you're comfortable with linear transformation, then this should not be difficult. This part. Okay, so yeah, so once you train it, you do this minimize reconstruction loss plus latent loss. Then you can just sample a z and you can get a new sample. Okay, that's this implicit generation mechanism for new samples. So of course, where is the data being used? The training data or your corpus data was used to get this network, not just this network, but the other side as well. Okay, I mean, not just the decoder, but the encoder as well. Okay, so these are parts of these are trained using data, and once you train it, this is how you generate new samples. And you can actually do this for images. It turns out that you get slightly blurry images, but you can actually do this for decently big images. And MNIST is what we saw a few slides ago. That's actually that code base is available on PyTorch's website, but there are other CIFAR 10 also they've done. You can just repeat. You don't even have to change anything. You can just run the same thing. Okay. Okay, so So VAEs were a little bit of a harder object. So I guess in summary, you know what autoencoders are. There's nothing probabilistic about autoencoders themselves. Given training data, get the embeddings. Okay, there is a very nice way to get embeddings for training data, and that's it. There is no sampling thing in just regular autoencoders. In variational autoencoders, you assume some latent variables which are z's. The encoded things are z's, and you assume some distributional assumption about something z condition on x is normally distributed, and x condition on z is normally distributed, and stuff like that. And with that, it turns out you can still train using this reparameterization trick, which we have not discussed at all. And once we train, we can get samples, like the Pokemon samples. That's the high level idea. And the only twist from autoencoders to, I guess, variational autoencoders in terms of objective function was an additional term, which was the scale divergence between the network's output, the encoder's output, and the Gaussian distribution. That's one additional regular, I guess, additional loss term that you had, this latent loss term, in addition to the usual reconstruction loss. That's the change. So let's talk about generative adversarial networks. So how many of you have heard of generative adversarial networks? Just 1, 2, 3. Has anybody else heard of generative adversarial networks? No? Or at least heard of the name, may not know the details. Okay, couple of more people. So so what is the idea? So again, we don't want to work with an explicit density function. We are not fitting like a Gaussian or a mixture of Gaussians. What we're going to do is there's going to be some way which is going to be game theoretic, but it's a way to get to again this object where I'll input some usual randomness like a Gaussian and get a output sample which is going to be interesting. So we'll some way to create this neural network in this case, because the neural network are the only fixed parts. Those are only parameters even in VAE. Just a decoder parameters and encoder parameters. Similarly here, there's going to be parameters, and that's the thing that I want to train using my data, such that object, if I pass in some random thing, it will give me an interesting sample. So, and the procedure is going to be game theoretic, by which, and before discussing the game theoretic idea, it's going to be that if my observation, so let's say X is an observation, if I sample observation from my data, sample just means, pick an observation from the data, don't worry too much about the sample, and there is a function, there's a function which, given this sample from data or this observation from the data, will try to evaluate to a number which is close to 1. This function d. It's called a differentiator, but basically, given a sample from my actual data, real data, it will evaluate to a number which is close to 1. So for all my data in my corpus, it will try to evaluate to 1. And the second scenario is, let's say I have some noise, let's say Gaussian noise. I pass it through this thing, which is going to be like the decoder, right? It will create some x, or basically it's equivalent to saying I got an observation from this model. It's not the data, but it's an observation from the model. If I pass it through the same function d, it actually tries to evaluate. Hopefully, it tries to evaluate close to 0. That's the idea. So it tries to evaluate the output of this guy, which got some random input, created a sample. D tries to make that that input g of z close to 0, whereas g itself, this function which is creating this interesting sample, is gonna update itself or change its numbers or change its parameters such that it can make d evaluate to 1. So that's the, I guess, trade-off or the conflict here. D wants to just use training data, make the training data evaluations to 1, and everything else to 0 essentially. And so everything else close to 0 just means that if some number was generated, some image was generated by G, for example, then it has to it wants to make it to 0. Whereas G itself will try to set its parameters such that it will try to make D evaluate to 1 instead of 0. Okay, that's the conflict. Okay. Actually, a better way to explain that is in the next slide. But what is G? So G is, I mean, we have already seen several instantiations of this thing. So given input Z, some sort of a randomness, like a Gaussian sample, G is some deterministic transformation, like a neural network, which will get to some image. Okay, so X is an image. Okay, and G is differentiable only because I want to do backprop and all that. And what is D? D operates on the image space or the X space, and it evaluates to either 0 or 1, hopefully. Okay, I mean, it evaluates to either 0 or 1. So here is a very simple one-dimensional example. Okay, so let's say these black dots are my data. Okay, so my black dots are my data, so it's a Gaussian distribution. Okay, for this Gaussian distribution, I want D to evaluate to 1. Okay, for this distribution. For any other type of data, I want it to evaluate to 0. So let's say I have a way to generate. So let's say there is a G of theta G. Oh my God, double G's. So let's say there's a way to go from some randomness, some source, let's say uniform distribution or something like that, to samples. If I draw their histogram, that looks like the green curve. Okay, so G, capital G, or this thing, starts from, let's say, uniform and creates a Gaussian distribution. Okay, and the Gaussian distribution is slightly different from the dotted distribution, which is my data. Okay, then what the D function is trying to do is to come up with some sort of threshold. So let's say this green curve is like this. Then all D is trying to do is to ensure that, okay, let me say 1 for all this and 0 for these guys. Okay, so basically, if here you can see that this part of the input region, the true, I guess this is the data part is high. There's a lot more data points on this side. So for that part, D is going to evaluate to 1. So that's this. Let's say this is 1, and you can see that in this part of the space, the G creates more samples, and so there I want D to be close to 0. So D is essentially a discriminator. It's essentially like in one dimension, it's basically differentiating between data drawn from the ground truth, like a histogram of the true corpus, and it's evaluating 0 for anything else that was generated. Okay, is the idea clear? What the objective of D and G are? So there's actually I guess a different viewpoint to just repeat the same thing, which is that the G, people call it generator network, I guess. So it's trying to fool the discriminator, the D function, by generating real-looking X's or real-looking images. What does it mean by trying to fool? Because you remember that this D function, and D function and the G function. So D function has to evaluate to 0 for things which are not in my training data. Okay, but the G network is trying to generate examples which are looking like training data, and therefore D is going to get fooled and will evaluate to 1. Okay, or so in simple English, basically G is trying to create samples which are looking like training data, and D is trying to distinguish between real and fake data. Real and fake just means real just means the one in my training corpus, and fake just means things which are generated by something else. Okay, so random noise, the usual network, the yellow block, remember, it's going to create some samples. I already have samples from my training data, and this guy has to figure out which is true, which is false, which is the right one, which is not the right one. Okay, and just as a high level point, if you drop the blue block, which is the discriminator block, okay, if you drop the discriminator block, you can actually compare samples from generator directly to the images, right? So I have a bunch of images in my training data. I'm creating samples from the generator, I can update the generator parameters such that these samples are close to each other. I can do some sort of reconstruction error, right? But that's not what's happening. The feedback, what we're doing is we're getting samples from the generator. We have the original samples. We are actually passing both to the discriminator, which is trying to discriminate between which is real and which is false. Okay, this is just a thinking that you need to have at the back of your mind. Okay. So again, a picture. Just to kind of set things, you have Z, which are again called latent random variables. I guess latent random variable. G is just a neural network, so let's say theta 1, and let's say this is theta 2, and you create a sample which is G of Z. Okay. Here there is no normality assumption in the sense of whatever Z is the source of randomness. So maybe you drew it from a uniform distribution or a Gaussian distribution, and then G is a deterministic transformation, gives you another random variable. Function of a random variable is a random variable, right? And you're just comparing these two, and discriminator hopefully can figure out which is which, and there is an appropriate loss function. So this is the block diagram. We'll get into the details of how the discriminator generator look like, and also how the loss function looks like, and how we're going to train these two networks. So there's going to be two networks similar to the VAE. There's going to be two networks, discriminator and generator, and we're going to update these parameters such that generator can fool the discriminator, and the discriminator will update its parameters such that it can distinguish between generated images and the true images. Okay, so that's the, I guess the game theoretic part is they are not aligned with each other, right? One is trying to like mislead the other. Okay, that's all I guess game theoretic means here. So what is the objective? So by which I mean just a loss function. Okay. The objective is going to be as follows. So remember PD was my data distribution. So histogram, just think of a histogram of my corpus, and PM was my model or generated data. Okay. So on average, on my on my real data PD, which is the data distribution, I want to maximize. I want to ensure that d of x evaluates to close to 1. Okay, so I'm thinking of a loss function, so I'm going to put a negative sign, but I'm going to minimize the negative of the expectation of the log of d of x. So remember, so it's trying to set these numbers to be high for my actual data p of d. Okay, so it's trying to set those numbers to be high, or the negative of that is setting those numbers to be low. Okay. Similarly, for the data generated from the model, I want to evaluate d of x to be close to 0, or the same thing as saying 1 minus d of x to be close to 1. Okay. So for model generated data, I want to set 1 minus d of x to be as high as possible, or the log of that to be as high as possible, or therefore if I put a negative sign in front of both of them, the same thing as saying I want to minimize this number over the model generated data. So over the PM, okay, the generated data. Okay. So two steps. One is to kind of, if you ignore the negative signs, it's basically saying on the real data, I want to make d of x close to 1, so log of dx is close to 1 or as high as possible. And for the second term, if you ignore the negative sign, it's saying for the generated data, I want to make log of 1 minus d of x as high as possible, or as close to 1 as possible. Okay, that's the objective function. Okay, but you'll see. So where is the So this is the objective of the discriminator, in the sense that discriminator is trying to set such that on the real data,
Why don't we have g of z in the equation in the second term?
Yeah, I mean there is going to be a g of z. I'm gonna show in the next slide that this d of x. So x is being generated from the model, right? So sorry. So instead of x, you can just write z of z and expectation with respect to z. Log of 1 minus d of g of z. If you're asking, yeah. Good question. So this was the objective of the discriminator. D is what it wants to set for real data. The d of x is close to 1, and for non-real data, it's trying to set it to close to 0, or 1 minus that close to 1, right? we're going to say that the objective of the generator is exactly the opposite. Okay, it's just saying that it's just minus of that original objective, so that whatever the discriminator is trying to do, I want to do the opposite. I want to ensure my samples are rated high or close to 1, and so the discriminator cannot figure out whether it's real or non-real. Okay. If you actually like, even at this level, if you just look at the, I put a lot of markings on this thing, but if this is the objective, if you take the first derivative with respect to I think D, expectation. Okay, so I'm trying to do some real-time computation, but all I'm trying to say is that if you set the first derivative of this objective function to be equal to 0, I didn't tell you exactly what derivative. I think it's with respect to D. Okay, so equal to 0, then you get D of x as a function of the two distributions. Okay, it's just the ratio of the data distribution and the model distribution. Okay, and similarly, you will set the objective of the generator to be, so if for the generator you can see there is nothing. First term doesn't involve anything to do with the generator. Second term is the only part which there is a G, right? There's this. First term has nothing to do with the generator. So if you set this generator, this objective Jg is equal to 0, then you will see that P of D is equal to P of M. Okay. So what the generator, so the best thing that the generator should do is to actually figure out what is the real data distribution and set it, try to generate that. Okay. And the best thing that the discriminator can do, if this is what the generator does, then the discriminator has no choice, right? I mean, if you substitute P of D, instead of P of M, if you do P of D, this is equal to 1/2. So discriminator doesn't know what is real or what is fake. Okay. So that's how I wanted to say that if you look at these objective functions, set it equal to 0, then the best thing that the generator can do and what is the best thing that discriminator can do is precisely this, which is discriminator cannot figure out what is real and fake, and the generator figures out that it has to generate samples, which is exactly the same as P of D. Okay, so just think of P of D as Gaussian. Then if that is Gaussian, then I have to generate Gaussian, same Gaussians. That's the moral of the story. Okay, so that's the objective, but this is just, I guess this is just for intuition, but basically the loss function is here. Okay, this is a loss function where D could have parameters, right, theta2 let's say, and G could have parameters, let's say theta1 over here. Then you want to optimize for theta1 and theta2, which is what we're gonna see now. It's quite straightforward. So what is it? So you first create a mini batch of real data, some batch. You create a mini batch of generated data at the current theta value, okay, some theta1. You score the discriminator. So given the current samples, you know what the objective, you can evaluate the objective, right? Remember there was an expectation over P of D. Instead of expectation, you have a mini batch, so you just take a sum over that, right? Then you score the discriminator, then you're going to update the parameters of the discriminator. Because we know there's a score with the current parameters, we can backprop to update the current parameters to some new parameters given the score. Okay. Similarly, we can score the generator as well. We can backprop. Sorry, let me call this beta g. So we can backprop to update theta g as well. The scoring function is the same. It's just negative of the previous one. So again, you have the score for the generator. You just backprop to update theta g. Okay. It's a pretty straightforward operation, except that two things are happening in tandem. One is you're updating the parameters of the discriminator, and then you're updating the parameters of the generator. That's all. I mean, this is just, I guess, a laborious way of saying what we just saw. This is what we saw before, and this is exactly what we saw before, where we now explicitly substitute Pg of theta of z. And okay, so the 2 slides ago, I was using a minus sign in the front, so there was a minimization problem for the discriminator. If there are no minus signs, the discriminator is supposed to maximize. And if the objective of the generator is the opposite, then the generator has to minimize. Okay, that's just a notation thing. And yeah, and as I said, for the generator, the first term doesn't matter because there is no theta g there. So for the generator, it's just the second term which matters. So generator is going to just minimize over the second term, and the discriminator is going to maximize over the whole term. Okay, that's it, and you update the parameters. Yeah.
So the goal of the generator is to produce as realistic as possible.
Yes. Yes. So we are implicitly trying to make the generator generate images which are as close to realistic images as possible. Yeah. So this is just saying, okay, freeze the generator, update the discriminator, and freeze the discriminator and update the generator. Okay, those are the two steps that we saw in the in the code. And what is the generator architecture? Again, it's the same architecture that we saw in the BAE or even the autoencoder. It's just it's called decon network or the transpose convolutional network, and the GAN which uses this type of a network is called DC GAN. Okay, it's from 2015 maybe, so 4 years ago. So where the operations here are essentially the decon operations, which I did not go into the details, but it's basically matrix vector multiplication, essentially equivalent to that. Okay. Okay, so once you have the network, let's say you train the network using this backprop, then here is an example of what you can do. Actually, remember, once you train the network, forget about the discriminator, keep the generator. What does the generator do? It goes from some z to some x, right? That's what the generator does. That's a yellow block. So what you can do is pick a particular z and actually evaluate by deterministically changing the z, by which I mean start with a z vector which is like a 0, 0, 0, then go to 0, 0, 1, maybe go to 0, 0, 2, and so on. So change it according, as a in a very deterministic sequential way. Okay, these are not random anymore. So these, if you change them in a nice way in some direction, for example, here they've shown if you change it in some direction, this is a bunch of, I guess this is trained on images of bedrooms, I think. So you have new images getting generated. So for each z value here, each z value, this is an x, this is an x, this is an x, and so on. And they're showing as you change the z value, maybe I don't know what dimensional vector it is, but as you change it, you get different images. Okay, and they look realistic enough to the actual, I guess, bedroom images in this case. And you can have other things like add goggles to, I guess, images and so on. Like basically you can get a z vector for this person, z vector for this person, z vector for this person, z1, z2, z3. Do the arithmetic and then you get another z vector. Just pass it through the GAN, so generator network, and you will generate these images. Okay, if you give some randomness to the z's. So let's not worry about mode collapse. Example. So actually, let me just so this script is again from PyTorch tutorial website. So the original source, the data set is available on the PyTorch as well as the syllabus page. I have the link. And so this may take some time. If you train, you can actually train this on our machines. Okay, so there's a lot of description about what GANs are. So we use what is called the Celeb A dataset. I guess, what is it called? Yeah, Celeb faces attributes dataset. Okay, so yeah, so some settings of the networks, but actually you'll see what the networks are. So you can download the data, and there is some manipulation that they're doing by using the dataset object in dataset function in torch vision, but and also use the data loaders. But basically here is a picture, a bunch of I guess pictures of the images in the data set. Okay, these are some small images, right, of people. Then okay, so weight initialization is not very critical. So generator. So what does the generator look like? So this is a generator. Okay, it's just a instead of con operations, there is a con transpose 2D instead of con 2D. So that's the NN module that you can call. So in fact, this is the definition. So you know how a NN module is extended, right? So you have an init function where you create different layers, and in the forward pass you pass the, given an input, you pass it through the operation, right? So in this case, self.main is a nn.sequential of all these layers. So they have used this way of describing. I mean, you can also go low level and explicitly describe what's happening in the operations. But these are the two parts, init and forward, for the generator. And this is the description of the generator. And similarly, the discriminator is also discriminator is going to be usual convolutional network. It's going to be, it's going from image to a number, right? It's a two. Think of it as two-class classification. Is it two-class? Oh no, it's just producing one number, nn.sigmoid. So yeah, so it's a usual convolutional neural network. It's getting an input image and it's going, doing con, I guess in this case, con leaky relu, con batch norm, sequence of those things, and you can change these to regular relus and so on. These are not hard and fast choices. I think this is a re-implementation of the 2015 paper, so that's why they've chosen this. Okay, but you can change this. You can make the networks actually even simpler. So for MNIST, for example, you can do MNIST. You can create a GAN for MNIST, and you can drop many of these layers and just have one con and one fully connected layer and be done. Okay, and don't have to have these so many layers. And you're just explaining what binary cross entropy loss is, but we know all that. So there's a loss function, and they're using Adam optimizers. So some of these you should probably have used in assignment 2. Okay. And then it's just a usual training loop. So where is the loss function? Oh, okay. So they used cross entropy loss for the discriminator because that's what the loss is. Okay. Okay. So there's a slight difference between. So this is a loss. Where is this? This is a loss that we saw even in the slides, right? So you can compute this. This is essentially the cross entropy or binary cross entropy loss. Okay, so the usual training loop, set gradients to 0. Few operations here, but basically compute the loss, take the gradients, and take the gradient step. Where is that? Yeah, optimizer.step is the actual gradient update. Okay, so in this case, what's happening is it's using the real data as well as the synthetically generated data from the network with some noise as input, and with both of them, it's getting the two parts of the error, right? And it's just taking I mean, for each part, they are explicitly calculating the gradients, and for each part, they're computing the gradients, and then they're updating the parameters of the discriminator for each part of the loss function. Okay, loss on the real data, loss on the generated data set. Okay, similarly, updating the generator. I mean, generator update is very similar to what you've already seen. I mean, is in the sense of you have yeah, I mean, so generator produces output through the current discriminator, and then look at the error backward and step. So these are some standard steps that you should have seen in convolutional neural networks. So, and I trained it, I think yesterday maybe, I don't know. Takes about half an hour. There's only, I think in this case, there were 5 epochs. And here is the loss during training. So loss, of course, hopefully decreases. Sometimes you will see actually, I mean, there are appropriate choices made in this particular script such that it actually converges. But in general, if you try, maybe you will have some divergence and so on. But you have to take care of that. And here is an interesting plot, which is trying to show the types of images being generated by the generator. Okay, so do half an hour of this task, and you're actually getting these generated images as the epochs are increasing. Okay, so initially it doesn't. It's basically generating noise, and it's starting to reproduce things which are very similar to the actual corpus. Okay, and so you can try this on the machines when you get a chance. There's one question, right? So why is the generator not just memorizing what my training data is, right? Like I have, let's say, 10 images, and I have high capacity neural networks, as in the sense that they're big neural networks. Then I can always, given enough time, I can actually just try to figure out how to reproduce those 10 images, right? So that can happen, but you have to restrict the capacity of the generator and the in this case generator, so that it's not just reproducing or remembering the images which are in the training data. Okay, so because the whole point is to generate new samples from this distribution over images. So distribution over real images is a highly complex thing. It's not clear what the distribution even looks like. It's not a normal distribution, right? It's not a mixture of Gaussians, for example. So there has to be some care taken that the generator doesn't overfit, essentially doesn't remember exactly what the training data is. So if you can do that, then this is this is an example output. Okay. Any questions about that? Yeah.
The purpose is, which discriminator is smart enough to discriminate, or generator should be able to discriminate?
Ideally, so think of the ideal situation where, let's say, the discriminator is not a neural network but a human. So if I've shown 2 images, right, I'm giving a score of so discriminator is basically trying to give feedback to the generator by saying, okay, your image is really bad, and that is the feedback. It's in terms of the loss function, but given that feedback, the generator is updating his thetas, right? So think of the ideal case where the discriminator is actually fixed and really good at figuring out what is real and what is fake. Then all you're trying to do is update the parameters of the generator such that I get fooled, or I'm not able to figure out what is real versus not real. Okay, so we are not trying to. So the end goal is not to create a really good discriminator, because although a really good discriminator is a byproduct of this training procedure, game theoretic training procedure, what we care about is the generator, because that's our implicit sampling mechanism or the implicit sampling method. Okay, like BAEs. So there are a couple of comparison points. I think I will let you read these 2 slides. There's a lot of text, but there is some. So it turns out in practice that GANs produce sharper images compared to VAEs, and it is kind of understandable because VAEs have this mean squared error type of a loss function. So it'll make images, even blurry images, may have good mean square error, whereas GANs somehow are, because of this very, I would say, indirect loss function, because the discriminator is scoring them as real or fake, it somehow is producing sharper images. Okay. So this is actually interesting. So VAs are part of graphical models, which are something, if we can get to, we'll get there. It's a part of at least in the syllabus it says we're going to talk about graphical models. So when we get there, we're going to talk more about variational inference and sampling and so on. Okay. Like if you just compare VAE and GAN side by side, basically once you have trained a GAN, okay, not trained a GAN, but you start with a random source, get an image, and hopefully the image is as close to the real image as possible. Here, you have an image corpus. So here also you have a corpus, which is this real images. You have image corpus, but you're trying to train the encoder and decoder such that you can do reconstruction really well and add some noise or randomness into the picture so that you can bring in new samples, right? That's the objective. But once you train them, you can drop the encoder here, you can drop the discriminator here, and you get new samples. Okay. So yeah, I mean, what is the applications, right? We saw, and they seem to be very nascent techniques, I would say recent techniques. So there are some applications: image denoising and image super resolution. Denoising just means removing artifacts in images. So maybe there is some text on top of an image. If you had a corpus of just images, then you would learn some patterns of these images such that you can remove the text on top of a given image at test time. Okay, so you can do that downstream operation if you had a good idea of getting samples from images, getting samples from distribution of images. Okay, and when I say reinforcement learning, just think of it as that scenario generation. You know, I can have, if I know what's going to happen, you know, in a self-driving car, what's going to happen 2 seconds, 5 seconds later, which is what I can get samples from by using GANs or something. Then I can take decisions, okay, actions. Yeah, so any questions so far about these two topics? What's the time? Any questions? So I would suggest definitely click through, as in try that celeb faces attributes dataset. See for yourself whether it makes sense. How at least that implemented version is called DC GAN, but there are many other GAN variations. Okay, I think last time I checked there was a GitHub repo on GAN architectures, and there were 100 plus architectures, which was just research papers, right? So I don't know if there could be 200 or 300 now. So try to look at that in practice so that you get more confident about what is a GAN doing. And VAE also, there's a script, maybe I'll share it on the forum. Okay. Any questions about these two? So after this, in the next lecture, which is after the exam, we'll probably look at PyTorch maybe in a little bit more detail, because today again I went through very quickly what a step operation is, what a backward operation is, and how does a nn.sequential, nn.module that we used here, as well as a few things like data loaders and dataset functions, right? So classes. So those maybe we'll spend some more time on them. Okay. With respect to exam, I think I've already clarified most of the questions. It should be relatively easy. So don't try to memorize too much. But at the same time, you should know so the dimensions of matrices, that they need to be matched, right? So if input is 10 dimensional, my first layer's matrix should not be, should not have more than 10 columns, for example, right? So those are things I should know. Yeah, so the syllabus would be up first 6 up to today, including GANs and VAEs, and the final exam will only cover the second.